Hello and welcome to this clip introducing dynamic equilibrium. So I'm going to look at what dynamic equilibrium means, describing in words the effects on the position of equilibrium, and Le Chatelier's principle. At certain points I'll ask you to pause and think about what we're talking about before continuing. So looking at dynamic equilibrium is basically the rate of forward reaction is the same as the rate of reverse reaction. Another key feature is the concentrations of products and reactants remain constant but aren't necessarily the same, and it takes place in a closed system. We'll look at this in a sec. So when we write out an equilibrium equation, we do the reactants on the left and products on the right as per normal, but we put a reversible sign between them. The forward reaction is taken to mean left to right, the reverse direction is taken to mean right to left. So a closed system is one where the particles can't get in and they can't get out. So it's sealed effectively. On the left hand side you can see the bottle is obviously unsealed, so it's an open system. The process of establishing equilibrium can be graphed. At the start there's only reactants, but as time goes on more and more product is made and more reactants is used up, until eventually their concentrations level out, and at that point equilibrium is achieved. You can see that their concentrations aren't the same as each other, but they are constant. The position of equilibrium is the relative quantities of reactants and products indicating the extent of a reversible reaction to equilibrium. If we start with the reactants being in greater concentration than the products, the position of equilibrium is shifted in favour of the reactants. The opposite is true where the products are in greater concentration than the reactants. The position of equilibrium is shifted in favour of the products. So what can be changed to affect the position of equilibrium? You might want to pause here and jot down what comes to mind. So pressure of a gas could be one of the things that's involved in the equilibrium. That can affect it. The temperature of the reaction can affect the position of equilibrium, and the concentration of an aqueous product, if it's in the aqueous phase, can also have a bearing on it. In this particular reaction we've got 1 mole of gas on the left and 2 moles of gas on the product side. So in this equilibrium either the forward or backward reaction can be favoured, so we say that the position of equilibrium can shift, and changing the conditions under which the reaction occurs can cause this. So let's look at changing the pressure. If we take two identically sized containers, in one we've got 5 moles of gas A at lower pressure, the other we've got 12 moles of gas B at higher pressure. If we imagine that these two can be mixed and put into one container, what I'd like you to do is to pause the clip and try and work out what the container will look like once the reaction is run to completion and equilibrium has been reached. So you might have come across something like this. 5 moles of AB formed, 7 moles of B left, 12 moles of gas in total, so therefore lower pressure. So let's go on to Le Chatelier's principle. If a change in conditions are applied to a dynamic equilibrium, the position of equilibrium will shift so as to cause that change. Pause the clip and see if you can have a think about how we can describe the effect of decreasing pressure. So, changing pressure at constant temperature, there are more moles of gas on the right hand side. So therefore, the decreasing in pressure will favour the side of the reaction with more gaseous moles. The position of equilibrium will shift to the right to oppose the pressure decrease by making more moles of gas. Now pause the video again and have a think about what's going to happen if we increase the pressure. Assuming you've done that, this time the pressure will favour the side of the reaction with less gaseous moles. The position of equilibrium will shift to the left to oppose the pressure increase by making less moles of gas. So now let's have a think about temperature. Forward reaction is endothermic. We know this because the delta RH value refers to the forward reaction unless otherwise stated. So the reverse reaction is exothermic. So pause it again for a bit longer to see if you can work out what's going to happen with these two changes, increased and decreased temperature. So I'm assuming you've had a think about that and come back to it now. With increasing the temperature, you'll favour the endothermic direction because you want to use up energy to oppose the temperature increase that's been imposed. However, with decreasing the temperature, you favour the exothermic direction because this time the position of equilibrium will shift to the left to oppose the decrease in temperature by releasing more energy. So with a catalyst, what happens is both directions will speed up to an equal amount. It will not cause the position of equilibrium to shift, and it will cause equilibrium to be reached more quickly. So the point at which equilibrium is reached will occur earlier in the region indicated with a catalyst. Thank you for listening and see you next time.